Okay, so hi everyone. My name is Haowen Zhang. So currently I am a graduate student at the University of Arizona and working with Peter Baruzzi. And here are all of my collaborators on Trinity. So today I'm gonna talk about another flavor of machine learning tools, which is data-driven empirical models. So specifically, I will just use our Trinity model of the halo versus galaxy and supermassive black hole connection from Redshift 0 to Redshift 10. I try to use that as an example to show that we can still get some new physical insights from data-driven empirical model that are easily interpretable and also robust. Okay, so firstly, some basic ideas about data-driven empirical model. We would start with typically in empirical models, we start with physically motivated latent spaces. So a common example is in the standard cosmology, where we have this like kind of simplified version of the latent space defined by omega matter, specifying the fraction of ordinary matter in the universe versus omega lambda that specifies the amount of dark energy in the universe. So these two parameters span the latent space that's really easily interpretable because they directly bear physical meanings. Okay, so what do we go about to constrain these two parameters? And that's going to be the second feature of empirical models, which is we have to use more than one or like typically many different kinds of data sets to break the degeneracies in the parameters that are describing our latent space. So if we want to study, say, how much ordinary matter versus dark energy there is in the universe, we certainly can use the type 1a supernovae data to see how much, say, dark matter plus baryon there is. But there's a huge degeneracy in terms of between the omega matter and omega lambda if we only look at the supernovae. So what we should do is that we have to include many different kinds of data, like cosmic microwave background and baryonic acoustic oscillation. When just inspected individually, yes, these data sets, they are still very degenerate in this parameter plane. But the good thing is that each of these three data sets, they're degenerate in very, very different directions. So if we intersect them with each other, we will suddenly get a much shrinked confidence intervals for both omega lambda and omega matter and omega lambda. And thus, we can break the degeneracies with the constraining power jointly from different data sets to figure out where our universe lies in this latent space. Okay, so now back to the connection between galaxies and black holes. What is the latent space that we're interested in this problem? So firstly, we certainly want to know what kind of black holes, how big are the black holes in different galaxies, and as well as how fast on average. And in addition to that, well, we may know that, okay, on average, over the past 1 gigayear, how much growth there was for black holes in certain galaxy populations. But we also want to know, like, the fraction of this certain period of time when the black holes are actively accreting versus being actually dormant, or in other words, inactive. So we also care about the duty cycles of those active black holes, or AGN. And finally, we want to know how fast black holes are growing, but at the end of the day, in real observations, what we observe are the AGN luminosities, which are not directly black hole accretion rates. So we need another dimension in this latent space, which is the radiative efficiency, to connect AGN luminosity, which is observable, to the physical black hole accretion rate. Okay, so this is our latent space, and next question is, okay, why do we even care how big the black holes should be in different galaxies? So in the local universe, we found that there are so many black holes in nearby galaxies, and on top of that, we also found a tight scaling relation between the black hole masses and the dynamical properties of these galaxies, like their central velocity dispersion or galaxy bulge mass. However, this scaling relation is really just well established only in the local universe, or redshift 0. Beyond redshift 0, you are hit by the fact that you cannot do high resolution spectroscopy to determine to measure black hole masses. You're also hit by the selection effects that black holes that are overmassive are more likely to be brighter and get into your sample more easily. So we really want to know what this scaling relation looks like at any higher redshift to understand the relative growth pace of galaxies versus supermassive black holes at different cosmic time. Okay, so this is black hole mass. What about black hole accretion rates? Why do we care about how fast the black holes should be accreting? Well, in the beyond the local universe, if we count the accretion of every supermassive black hole and count the star formation in every galaxy, we know that the cosmic black hole accretion rate density and the cosmic galaxy star formation rate density are proportional to each other. So this could be an indication of something like coevolution or correlation between the two growth channels. However, we do not know like how fast, we do not know how this ratio changes as a function of different galaxy populations, say in 10 to the 9 solar mass galaxies versus 10 to the 11 solar mass galaxies, how different are black hole accretion rate versus star formation rate ratios. So why is this important? Because in lots of theoretical models like hydrodynamical simulations and semi-analytical models, black hole feedbacks are very commonly involved to reproduce the properties of high mass galaxies. And the AGN feedback mode, or black hole feedback mode, is a strong function of your the specific black hole accretion rate, which is the black hole accretion rate divided by the black hole mass itself, or effectively just the Eddington ratio of black holes. And more specifically, if you have lower Eddington ratio or lower specific black hole accretion rate, it is more likely to be like the dominant black hole feedback is more likely to be kinetic, meaning that more kinetic energy than radiation is going to be imparted to the surrounding area of accreting black holes. So in order to know the dominant feedback mode that are actually happening in the real universe, we really need to know not only the black hole accretion rate, but also the black hole mass for every galaxy population at any given redshift. Okay. So basically, to figure out how the galaxies and black holes really populate this latent space, we built Trinity. So what Trinity does is that it firstly put galaxies and supermassive black holes into their host dark matter halos, and then evolve these three ingredients self-consistently along the halo assembly histories. In this process, Trinity tries to match try to figure out the connection between, all right. So in this process, Trinity tries to figure out the connection between halos, galaxies, and black holes that can match all these different kinds of galaxy and supermassive black hole data to break various degeneracies. So, for example, if we start with the galaxy star formation histories in different halo populations, which are constrained by, say, Peter's universe machine model, we can then use the quasar luminosity distributions for different galaxy populations to specify the black hole accretion rate histories for different galaxy or halo populations at any given redshift. Except there's a caveat, being that we directly observe quasar luminosities, but here what we are really caring about are the accretion rates. So these accretion rate histories can, in principle, be shifted up or down based on your assumption on the AGN radiative efficiency. So to break this degeneracy, we further anchor these accretion rate histories using the local galaxy bulge mass versus black hole mass relation. It basically figures out, it basically specifies how much black hole mass should there be at the end of each of these black hole accretion rate histories. And it basically specifies the normalization of these black hole accretion rate histories. And once we figure that out, we get a full constraint, not only on the normalization, but also the shape of such accretion rate histories, and also the constraint on the AGN radiative efficiencies. Okay, so this is just an example of how Trinity breaks the various degeneracies using both luminosity constraints and the mass constraints for supermassive black holes. Okay, so in addition to these data, to provide as much information as possible to our model, we have compiled a unique galaxy plus AGN dataset with lots of different different kinds of data across a large redshift range. So for the galaxy part, we use stellar mass functions, specific star formation rates, cosmic star formation rate densities, galaxy quench fractions, and even UV luminosity functions at really high redshift to specify what kind of galaxies should be living in what kind of dark matter halos and how fast they should be forming stars at any given cosmic time. So for the AGN part, we firstly included the quasar luminosity functions and quasar probability distribution functions from X-ray surveys to specify, firstly, the total energy output of all the supermassive black holes, and also how this total energy is supposed to be distributed or allocated among different galaxy or supermassive black hole populations. And as I said, these are luminosity constraints. We also need mass constraints to break the degeneracy between the AGN efficiency and black hole accretion rate. So we have included as well the quasar black hole mass functions and also the local black hole mass versus bulge mass scaling relation to anchor the amount of black hole mass in place that are produced by all these black hole accretion processes. Okay. So by matching all these data, the first prediction that we can make is the mass connection between black holes and galaxies across the cosmic time. And based on our best fitting model, it seems that this mass scaling relation doesn't evolve a lot across from redshift 0 to redshift 10. And even beyond that, Trinity actually effectively creates a unique map between our observational data input and our model predictions. So using this map, if you have proposed any alternative redshift evolution of the black hole mass versus galaxy mass relation, this map would tell you, well, which part of the data constraint are you violating? And it will just tell you how we would reject your proposed alternative redshift evolution of the mass scaling. And vice versa, this map also tells you how much or like in what way our prediction will change in response to any of our change in the data input. So this basically tells you, this basically gives us a understandable change. Sorry, it makes any change in the model predictions understandable in response to the input data change. Okay, so beyond mass connection, Trinity also tells you the Eddington ratio distribution, or effectively how fast the black holes are growing in different halo or galaxy populations at any given redshift or cosmic time. So at high redshift, regardless of host halo or galaxy mass or black hole mass, we see that the black holes are accreting on average at around the Eddington rate. And this Eddington ratio starts declining once you go to lower and lower redshift universe. And this decline actually starts among the most massive objects. And gradually, this decline starts to appear in also less and less massive objects, which is also consistent with the observed phenomena called AGN downsizing effect. And in the really like massive regime and really low redshift universe, we also see that the Eddington ratios of black holes are generally very low. And this is also consistent with the scenario that the supermassive black holes, because low Eddington ratios are typically associated with the so-called kinetic feedback, where supermassive black holes inject more kinetic energy than radiation to its surrounding environment and serve to quench the star formation in their host massive host galaxies. Yeah. Okay. So if we combine the mass connection between galaxies and black holes with their Eddington ratio distributions, we can actually use Trinity to better understand our current and upcoming observations of high redshift supermassive black hole populations. So historically, we have discovered quite a few, well, actually many high redshift quasars. They are like, say, at redshift above 6. And it's interesting that they seem to be overmassive compared to their host galaxies. If you assume that the galaxy mass versus black hole mass relation doesn't change much from redshift 0 to redshift 6. But apparently there's a, qualitatively, there's a selection bias in the sense that with the same Eddington ratio distribution, more massive black holes are naturally brighter because luminosity is just mass multiplied by the Eddington ratio. And brighter objects are like way easier to get into our flux limited sample at high redshift. You can actually also see this by just checking out the color maps of these individual data points, in the sense that redder data points, they tend to like populate the upper region of this black hole mass versus galaxy mass parameter space. And now with the outputs from Trinity, we actually are able to quantify, okay, as a function of limiting quasar luminosity, how big this bias is as a function for quasar populations above different luminosity limits. So you can see that here's a huge gap between the faint AGN populations above 10 to the 45 ergs per second compared to the brightest quasars above 10 to the 48 ergs per second at redshift 8.7. And for comparison, the black solid line here is the intrinsic scaling relation at the same redshift for all the black holes. So if you want to study the intrinsic scaling relation at redshift 8.7, you really need to be focused on these faint AGN populations. So is that possible? Well, before JWST, it is really difficult. However, last week, the SEER team have published this surprising result, a redshift 8.7 AGN with a very faint luminosity. So I guess finally we are able to probe these faint AGN to study the high redshift intrinsic scalings between black hole mass and galaxy mass. And I hope in the upcoming, say, like in the near future, we will get even more data points from either SEERS or other team with JWST to provide more tests on our Trinity model. Okay, so I think I'm running out of time. Just want to briefly mention that Trinity also predicts the host halo mass distributions for any supermassive black hole population. And these host halo mass distributions actually make sense because we also check AGN clustering signals and compare them with observations, and they match really well. Okay, so I guess in the interest of time, I'll just leave the summary here and I will take questions. Yeah, thanks.
John, questions? Okay, I'll get us started then. Yes. So it seems like you're connecting the, I guess, the black hole primarily to the galaxy, like through the black hole mass, stellar mass. Is there anything indicating that there might be some, I guess, intrinsic connection between the black hole and the halo that is independent of the stellar mass of the galaxy?
Yeah. So in the current version of Trinity model, we connect dark matter halos and black holes only through their galaxy properties, and more specifically, galaxy mass. So there is no direct connection between halos and black holes beyond their mutual connection with the galaxies. Yeah.
Okay, more questions.
Hi, Megan Tillman. I just had a question about, so your main result, one of your main results is finding that the supermassive black hole mass and galaxy mass scaling relation is, there's not much evolution.
Right.
But I was under the impression there was a lot of studies that were talking about how you can't really expand the like local relation that we see to higher redshifts and to lower mass galaxies.
Yes, exactly. Yeah. So
so are you finding one that's just completely different than the local one we see, or?
So basically, I think for at least for the situation at high redshift, the main, I guess the short answer is there's a lot of selection bias, because in the high redshift universe, typically you can only observe those very bright quasars, and because bright quasars, so at high redshift, the Eddington ratios of black holes are really similar, regardless of their masses. So more massive supermassive black holes that are naturally more likely to be brighter, right? Because the Eddington ratio is the same. So they're more likely to get into your sample and just thus bias the whole like black hole mass versus galaxy mass scaling relation. this is also shown here, like, basically, the brighter you are as a quasar, the more likely you are to like be overmassive compared to the fainter ones. Yeah, right. And yeah, go ahead.
I was just gonna follow up.
Yeah.
I probably missed this. Why is it that all black holes at higher redshift have about the same Eddington ratio?
Yeah, so I think this is basically, I guess mathematically, this is determined by the fact that so generally, we do see higher and higher Eddington ratio towards higher redshifts. This is constrained by our data set. We have another constraint that, okay, so at high redshifts, you do not really see you do not see many super Eddington objects. So basically, you need to have like higher and higher Eddington ratio towards the higher redshift, and yet you cannot, you don't see many super Eddington objects. So basically, all the black holes, they are like their Eddington ratio distributions are like shifted higher and higher, and also like getting narrower and narrower. So that's what we see in the Trinity model. Yeah. And physically, this could be due to the fact that, okay, at high redshift, the Eddington rate is actually roughly where the rate at which the post-dark matter halos and galaxies are growing at. So there could be some like physical connection between like, there could be some like correlations between the halo growth, galaxy growth, and the supermassive black hole growth at such high redshift that's causing the three to be growing at this, roughly the same Eddington rate. Yeah.
Right. So, Sucheta Kure, so in your Eddington ratio plot,
Yeah.
as a function of halo mass, yeah, I think that one, the previous one.
Yeah.
Yeah. So you said that the ratios go down with redshift, but I see for example, higher peak mass, there's a slight increase.
Yes.
Do you have any physical implications or like guess as to what's happening?
So this actually comes from one of our data constraints. So it basically specifies the amount of energy that should be in place specifically for these massive galaxies. So you need those residual accretion to account for basically the AGN luminosities in these massive galaxies. Yeah. So physically speaking, it means that, okay, the black holes should be, there should be some residual growth in these black holes in order to match the real observations in the X-rays. Yeah.
Right, but I mean, I understand why it would come observationally, but if you have like, is it because of like additional gas accretion, that like rejuvenation type of scenario that happens for massive galaxies at low redshifts, or that could be an option, I guess?
Yeah, I think like residual gas could be a potential source of the black hole accretions for these low redshift and massive galaxies. Yeah.
Great. More questions?
Richie Wong here.
Yeah.
Also regarding this plot, do you think that, since now you have a constraint on the Eddington ratio and how, say, the kinetic versus quasar mode feedback should evolve, do you think it should be implemented for tuning HydroSim's AGN models with your constraints?
I would be a bit cautious about that because currently we are trying to, currently we do not have any like constraints on the kinetic energy outputs from the that gets input into our Trinity model, but instead we use an empirically determined like conversion between the total Eddington ratio and kinetic Eddington ratio and radiative Eddington ratio. So basically, there's an empirical conversion between the total AGN energy output and its component in radiation versus kinetic energy. This comes from the observations in radio wavebands and X-ray. I'm not sure how the people doing simulations would trust this empirically determined conversion. So I would like to get more observations in these two like wavebands to get a better constraint before talking about like actually using our results to implement the subgrid physics in the simulations. I mean, specifically about the kinetic versus radiative components. Yeah.
So I think that's equivalent to say that in your current model, the strength of your constrained Eddington ratios does not back react and suppress galaxy growth, right?
Sorry, could you
like your black hole growth is totally determined by galaxy growth, and if your black hole is just accreting more and having more violent feedback, it doesn't suppress galaxy growth in your model.
I guess yes and no, because our model does have the flexibilities to make the galaxy the black hole grow while the galaxy star formation is quenched. It's just that I flexibility to like quench the galaxy star formation while keep the black hole growing. Yeah.
Okay.
Right.
Yeah, thank you, Owen.
Yeah.
Smart World Company. I was wondering if you can go back and from your results, you can identify which are the observables that are more, driving, constraining.
Exactly.
And, and so it's a way of measuring the robustness of these, right?
Yeah.
Kind of taking a gradient or knowing, okay, if I remove this data point, then, my constraint on the relation changes.
Yep.
And if you can identify then what observables I should constrain more, for example.
Exactly. Yeah. So we actually did some tests on, say, if we add more high redshift quasar luminosity functions. Of course, they are simulated. Say, simulated redshift 6 to redshift 10 quasar luminosity functions from, say, Euclid or Roman. We can actually get much better constraints for the black hole masses above redshift 6. So basically, if you have those quasar luminosity functions, you can shrink the mass uncertainty of black holes from maybe like 0.7 dex to about 0.3 dex, even at high redshift. So that's something that Trinity can do as well.
And then, but for example, I was wondering about the robustness. So is there anything that you can say, okay, if I get more constraint or more data point on this regime, my constraint on the M sigma relation can change or not, or M star, M black hole can change. For example, I can find some evolution that you don't find because, something like that.
Exactly.
Yes. So this but can it change somehow, or is it robust enough that you say with the data we have, there's no room now for any significant evolution of the black hole mass relation?
I think there's always some there's always a limit in the extent that you can like keep your result like qualitatively unchanged given like despite the change in the data. But I think at least for the high redshift quasar luminosity functions, I don't like adding any like reasonably simulated quasar luminosity functions doesn't really change our result. It just shrinks our mass uncertainty at high redshift. Yeah, to a great extent. Yeah.
Well, thank you very much, Helen.
Right.
We have to move on to our lightning talks, but let's give another round of applause.